So yesterday we talked about everything with vertical rectangles. We talked about if the top or the bottom changes, you need a new integral. And our focus should be top minus bottom, and everything is in terms of x. And that was wonderful, except today we're going to talk about horizontal rectangles. So you're asking yourself, why would I want to do that? The vertical rectangles were working just fine. And for the most part, they will work just fine. If you want to go into the horizontal rectangles kicking and fighting and saying, I'm never going to do this, you can. But I'll demonstrate in this first example why your life would be made a lot easier if you also get behind the horizontal rectangle possibilities. So the vertical rectangles, everything was in terms of x. Our equations were written in terms of x. We had a dx on the end of the integral. Our limits of integration were relating to the x values of the points. Today, everything flips over, and now everything becomes based on y. We start with a horizontal rectangle. Our equations are written in terms of y. We have a dy on the end, and our limits of integration are y values from the points. But again, why? Okay, well, here's an example. I have two graphs. Notice they're not functions. Why aren't they functions? The other one. They don't pass the vertical line test. These are not functions. But that's okay, because there's still an area there that we can find the area of. And it's color-coded. The blue sideways parabola is the equation written in blue. The red sideways parabola is the red equation. So if you wanted to do this with vertical rectangles, pop quiz, how many rectangles would you need? No? Well, okay, hold on, yes. Yes, you would get infinite. How many, I asked the question wrong. How many representative rectangles would you need? No? You could just keep counting out. One didn't work, let's try two. Two? No. Three, excellent. You guys are so smart. They would look like that. Yep.
That makes sense.
Yeah, of course.
We should have thought about it.
Now, if I was going to do this using vertical rectangles, the first problem I would run into is these are not in terms of x. Those are in terms of y. So I'd have to solve this for y. Y, whoops, I have the wrong color. Y is equal to plus or minus the square root of x. Y plus or minus, because when you take the square root, you get plus or minus. If I just graph the square root of x, I'm only going to get the top part of the curve. I want the whole curve, so you need a plus or a minus, which means if I'm talking about the top part of the red curve, I'm using the positive square root of x. If I'm talking about the bottom part of the curve, I'm using the negative square root of x. Same thing is true over here. If I solve that for y, I end up with y is equal to plus or minus the square root of x over 2 plus 2. Lovely. The positive part is the top part of the blue curve. The bottom part is the negative part of the curve. And then I've got to set up 3 different integrals. Is it doable? Yes. Is it ugly? You bet it is. So I would suggest that that's not the way to go. But again, last time I checked, this was America. And if you want to use vertical rectangles, then by all means, fight the power right on. However, I would try to encourage you to use one single horizontal rectangle. Only one is needed. Why only one? Well, we're no longer dealing with top and bottom. We're dealing with right and left. And notice, over that whole shaded region, the right side is always the blue curve. Sorry, the right side is always the red curve. The left side is always the blue curve. Since there's no change there, we can just do one representative rectangle. The functions are already given in terms of y. What I need, however, are my limits of integration. When I set up my one integral, what would I go from? And what would I go to? What's my lower limit of integration?
From -2 to 2.
Say again?
-2 to 2.
Perfect. lowest horizontal rectangle would happen at -2, the highest negative, or the horizontal rectangle would happen at +2. Those become our limits of integration. Now you can assume from the graph that those points are 1, 2, 3, 4, 4, 2, and 4, -2, but sometimes you won't have a picture, or you may have to do like you did on the worksheet we just finished, and solve for those points of intersection. So I found the y values. And I kind of glanced over it, but notice top minus bottom becomes right minus left now. If I want to know how long that yellow rectangle is, it's the right value minus the left value. Everything else is just like we did yesterday, except for a couple small changes. We know the points of intersection, and everything has to be in terms of y. Our equations are written in terms of y. Our limits of integration are the y values of the points. We have a dy at the end of it, because that's the height of that rectangle. Really, really tiny. So we get to, that's the area of the rectangle if you're bothering with that now. And if you want to jump right into the integral, we would get that. So you're saying to yourself, how do I FN int that? Is that what you were going to ask?
Yeah.
You have two options. The calculator is smart enough that you could use y's as long as you put a dy at the end. But that means you have to go alpha y every time. If you just replace the y's with x's, it'll give you the same answer. So in other words, if you do the integral from -2 to 2 of x squared minus 2x squared minus 4 dx, it's just taking that picture and turning it up 90 degrees, the area stays the same. And I don't know what the answer is, nor do I care. That's not what this is all about. The difficulty comes out of these one of these three situations. Here's a problem, solve it in terms of x. Here's a problem, solve it in terms of y. Those are pretty straightforward. The difficult one is the third question is, find the area of this region, use whichever method you want. You're going to have to figure out, am I better off doing horizontal or vertical rectangles? And it's up to you. Some of you are not going to want to do horizontal. You're going to find it too confusing, and you're just going to fight to do verticals. That's okay. It just may be a little bit more work. You can use whichever one you want. The answers will be the same, assuming you do them both correctly. So, if we're dealing with vertical rectangles, you've got top minus bottom for the area of that rectangle. If we're dealing with horizontal rectangles, you've got right minus left. You got to keep track of which one is which. Questions? Go.
I guess it's just kind of a general question, but what do you do with area under the x-axis when you're doing this stuff? Because we're not subtracting it anymore, are we?
That's positive area.
Okay.
Area is area now, so we're going back to more of a geometry model where area is area.
Sure. And wait, so does that mean when we just happen into it all works out, right? We don't need to worry about like absolute value.
Nope, it works itself out.
Okay, but if we were to solve it, then we would.
It'd still work itself out.
Okay.
Yep. Good. Now you will, when you were doing last night's homework, there were some problems that said, A, solve this in terms of x, B, solve this in terms of y. Obviously, we didn't do the y stuff yesterday, so on top of day 105, you're also going to have to go back to day 104 and include the y parts of those problems that we did yesterday, which is also why I'm not collecting day 104 today. Questions? Go.
Just ask a question.